Okay, so in the second half of Lecture 5, we're going to take a look at arrays and also at for loops, which is an alternative to the while loop, and we'll use that for stepping through the items in an array. Now, an array of n objects in C++ has to be specified with the data type of thing that the array contains. All right, that's what we give first. Then we select a variable name that we want for our array. And then in square brackets, we put n, the number of items that we want to have in that array. And of course, our closing semicolon for the statement terminator. All right, now casually, because we're using square brackets here, this looks sort of kind of a little bit like Python lists, but it's also very different from that in many, many ways. First of all, this array that we have declared is only able to contain values of the particular data type specified. Whereas in a Python list, of course, we can have a mixture of different data types. Over here, in this example program, we have declared that A is an array of 4 ints. So A can only contain ints, and specifically it contains 4 of them. So a second difference between arrays in C++ and lists in Python is that this array is of fixed size. It cannot grow and shrink the way lists in Python do. It does contain 4 ints. It will always contain 4 ints as long as it exists. In this case, this A array is a local variable within the main function, and it turns out it will be created as soon as the main function is called, and it will be deallocated as soon as the main function returns. Elements within an array are indexed from 0 up through n-1. We don't have, as we do in Python, -1 as an index for the last element in the array. It turns out we can use negative subscripts, but they are treated in a quite different way in C++ than they are in Python. We can initialize arrays or leave them uninitialized. I recommend to follow the rule that all objects should be initialized whenever possible, and this applies to arrays as well. In the C++ language, we use curly braces to contain the sequence of initial values that are put into the array. So here, in this example program on slide 12, we say A is an array of 4 ints, initialized with, and here I'm reading this equal sign because this is a declaration of the array A. This is not an assignment, so I'm calling this the initialization sign. A is an array of 4 ints, initialized with the values 2, 3, 5, and 7. Now, in recent versions of C++, you can, it turns out, leave out that equal sign in between the declaration of the array and the list of initial values that are stored into the array. You'll see this written in either of those two ways. Now, you can have arrays of almost anything that you want in C++. You can have arrays of ints, arrays of chars, arrays of doubles, arrays of ints, arrays of doubles, and so on. One example of something that you can't have is you can't have an array of void. All right, so void has no value, occupies no memory. If you attempt to declare an array of void, the compiler is going to scream at you about that. Okay, so let's take a little more of a look at this program here on slide 12. In fact, I'm going to pull that up in my Ubuntu environment. The name of this thing is arrayswhile.cpp. Here we go. Here I've got my comment for the name. I'm including IOStream and using namespace standard. Now on slide 12 there isn't actually quite room for that stuff, so I've left out the the include and the using namespace stuff. But these programs are the same. I here is actually going to be my counter for my while loop that I'm going to use to step through the array. And I want to initialize I to 0 basically for two reasons. First of all, you should always initialize any object that's used in your program whenever you can. Second of all, the initial subscript as I step through the elements in an array is going to be 0. So initializing I to 0 both accomplishes initialization, which is an inherently good thing to do, and also initializes I to be 0, which will be the first subscript in my array. Okay, A is an array of 4 ints. Initially, the elements in A are 2, 3, 5, and 7. This is the old C language style of initialization notation. B is likewise an array of 4 ints. It's initialized with elements 11, 13, 17, and 19. I'm using the C++11 style initialization here by just leaving out the equal sign. Now, I want to display the items in A. So, I'm saying while I, my subscript variable, is less than 4, we would typically use a less than test for a subscript because if 4 is the size of the array, the element subscripts go from 0 up to 3. So while I is less than 4, let's display A sub I square bracket colon. All right, so this is just showing us which element is being displayed. And then the actual element value. If we take a look at the output of this program on the next slide, this first line of output is going to display A sub 0 colon space. All right, that's this A sub 0 colon space. And then the value of A sub 0, which of course is 2. And a new line, so the cursor goes down to the beginning of the next line. Now, we increase I by 1, so that the next time through the loop, I's value is 1. And 1, of course, is less than 4, so we display A sub 1 in this case, is 3. We increment I and loop through again and display A sub 2 is 5. Increment and loop again, A sub 3 is 7. Now, when we increment, this time, I will become equal to 4. And since 4 is not less than 4, the loop fails at this point. The test expression fails at this point, and I drop down below the while loop. I have used curly braces here because my while loop has two statements within it, and I need to use curly braces to ensure that both of those statements are understood to be controlled by the while loop. If I left the curly braces out, and we're thinking, as in Python, that the indentation was going to make things work, well, unfortunately not. Even though this line I plus gets 1 is indented, if I left the curly braces out, the C++ compiler would assume that I plus gets 1 is below the bottom of the while loop. And I would end up having an infinite loop that was displaying A sub 0 over and over and over again because I was never being incremented in that case. Okay, so get in a habit of using curly braces in decisions and loops, even when not strictly necessary, and that will save you from some silly bugs. All right, after the first while loop, I's value is 4. We want to go through and display the items, the elements in B next. So we'd better remember to reset our subscript variable back to 0. Of course, that's an easy thing to forget. If you forget, then since I is still 4, 4 less than 4 will fail, and you will not display B, which will be puzzling. All right, so you got to remember to reset your loop variable. And then this while loop performs exactly the same way as the previous while loop. The only difference is that we're displaying items from in C++, we talk about array elements, whereas in Python we talk about array items. I have no idea why, but I'm going to try to be consistent. Okay, so we're displaying elements from B here. B sub 0 is going to be 11. B sub 1 is 13. All right, and we can see the output over here on slide 13. So B sub 0 is 11. B sub 1 is 13. B sub 2 is 17. B sub 3 is 19. Let's just confirm that that's what we get. I'm going to save this, and I'm going to compile it. There we go. Yay, it compiles. I didn't make any stupid typos. And it runs, and we get the output that's shown on slide 13. All right, so no big surprise. Next up, we're going to introduce the for loop, which is more commonly used for purposes such as iterating through the items within an array. The while loop is a little bit awkward because we need to do the initialization of the loop control variable before the loop starts, and we need to do the increment of that loop variable at the bottom of the while loop. Now, in this case, it's not too bad because the while loop is relatively short. So we're saying I get 0, while I is less than 4, display b sub I, and then the value of the element b sub I, and then add 1 to I. But I promise you, no matter how long I've been writing C++ code, that I regularly forget either to initialize the variable I want to use in my control expression, and or I forget to add 1 to I at the bottom of the while loop. This is a very common bug even for experienced programmers. It turns out that the for loop is more reliable than the while loop because all of the loop control stuff is right at the top of the for loop. So it's much harder to forget what you're supposed to be doing. Here is our outline of a while loop. Okay, we're initializing some variable first, and then while some test expression, typically involving that loop variable, is true, we're going to perform some body of code, and then at the very bottom of the while loop, we will change that loop variable. The for loop equivalent for this is you have the initialization part as the first of these 3 expressions in the for loop structure. Then you have the test, which is the same as the test that you would have for the while. If the test succeeds, the body of code is performed. And after the body of code is performed, then the change expression is performed. Once the change expression has been performed, we reevaluate the test expression. If the test expression is still true, we execute the body and then the change, and then reevaluate the test. If it's true, we do the body, change, test, body, change, test, body, change, until eventually, we hope, that the test becomes false, at which point the for loop is over. So to repeat what I just said there, the initialization part happens once and only once. After the initialization part has taken place, the test is performed second. If the test is true, the body is performed third. And if after the body has been executed, even though the change is positioned above the body in terms of the structure of your code, the change is actually executed fourth. Okay, so we've got initialization once, then test, then body, then change, test, body, change, test, body, change, test, body, change, until eventually test becomes false and we drop out. Okay, so on slide 16, we have the for loop equivalent of the program that we showed for using the while loop. Okay, let me, in fact, on my left-hand slide, let's put back the while loop version of this. Okay, so there's slide 12, and in my Ubuntu environment, I want to show the for loop version of this code. All right, so we've got our array name as in a comment, include on a stream using namespace standard. Then we have our main function here. In the top part of the main function, we're declaring and initializing our loop variable to 0. Then we are saying A is an array of 4 ints, and we're specifying the initial value for those 4 int elements. B is an array of 4 ints, and we're specifying the values for those 4 int elements in B. And now, notice how we're writing the for loop. The first thing we do in our for loop is what's called the initialization part. In this case, because we're using an integer subscript to step through the array, we're assigning I equal to 0 in the initialization expression. Now, we had actually initialized I in I's declaration up here to be 0, but one of the benefits of the for loop is we don't even have to remember what we did up above. We'll just go ahead and set I equal to 0 here, because we know at this point while we're writing our code that we want to step through items in A starting from sub 0 up to 1 less than 4. All right, so we initialize I. We then test whether I is less than 4. Of course, I is less than 4 at this point. So we display A sub 0 as a string, and then the element value A sub 0, which is 2. And after the body has been performed, then we do the change part. Now, notice that syntactically, the change part comes above the body, and yet the change part is still executed fourth. It's the fourth thing that happens. All right, so we do initialization once, then test, body, change, test, body, change, test, body, change. After we've gone through the loop 4 times, I will have been incremented to 4, and when we do the test, I will be equal to 4, the test will fail, and we'll drop out of the for loop. This particular for loop's body is only a single statement, but for stylistic and maintainability reasons, I have done as I recommend that you do. I have used curly braces around that body, even though in this case it isn't strictly necessary. In the second for loop, I have not used the curly braces, again, because the body is only a single statement. And it's really up to you to decide whether you're willing to use the curly braces all the time or whether you only want to use the curly braces when strictly necessary. It's a matter of taste. I personally believe that using the curly braces consistently will save you from silly mistakes, especially earlier in your C++ programming career. All right, the second for loop has the same initialization. We're saying I gets 0 to begin with. Then we're displaying B sub 0 is, and then the element value B sub 0, which is 11. I gets I plus 1. 1 is still less than 4, so we'll display the next value, increment I, and so on. And so the output of that program is exactly the same as the output that we had for the while loop version of the code. Let me just compile and execute this to prove that. All right, here's my arrays for loop code. I'm going to compile it. And run it. And it works. Okay. All right, so we have taken a look at how to declare and initialize arrays. Both of our example arrays were arrays of 4 ints. And we've looked at using either a while loop or a for loop to step through all of the elements within the array. And in our case, all we did was print those out. Now, array elements in C++ code are stored in ascending contiguous, that is, side by side, Memory locations. This is completely unlike Python, where what is stored in a list is actually references to values, and those values could be anywhere in memory. So if you have a list containing 2, 3, 5, 7 in Python, there's no implication at all that the 2 and the 3 and the 5 and the 7 are stored anywhere near each other in memory. They could be stored any old place in the machine, and what the what the list actually contains in Python is references to those values. In C++, it's guaranteed, for example, here's my array of ints. IA is an array of 4 ints. It's guaranteed that I'm going to have 4 ints worth of memory directly side by side. Each int in C++ is probably going to be 4 bytes wide. So element sub 0 is going to be 4 bytes of memory. Element sub 1 is going to be 4 bytes of memory immediately following element sub 0. Element sub 2 is going to be 4 bytes immediately following element sub 1. And element sub 3 is going to immediately follow element sub 2. Who cares? Well, the reason we care is that the way processors work, it's more efficient to access contiguous memory than it is to access memory that's all over the place. Most modern processors have what's called a cache right on the chip that's more efficient to access than main memory. And reasonable sized arrays will typically fit right in the cache and be able to be accessed extremely efficiently by virtue of the elements being side by side or contiguous in memory. Now, if we have an array of characters, each character in C++ is guaranteed to occupy exactly 1 byte of storage. So for sure, if an integer is 4 bytes wide, it's going to be the case that an array of 7 characters is going to occupy 7 bytes of space. That is, we can fit 4 characters into the same amount of storage that we can fit 1 int. A double, on the other hand, here DA is declared as an array of 3 doubles. A double on your system is probably 8 bytes. That is, it occupies twice as much storage as an int does. And in this array of 3 doubles, we have double sub 0, double sub 1, double sub 2 in sequential side-by-side, that is, contiguous memory locations. Okay, so that's an important efficiency thing about C++. Now, another aspect of C++ arrays that will distress you if you're comfortable with languages like Python and Java is that C++ does not do any array bounds checking. If you have an array of 4 ints, okay, here A is an array of 4 ints, and it's been initialized with 2, 3, 5, and 7. 2, 3, 5, and 7. And if you forget that the subscripts for that go from 0 to 3, and instead, for example, write a for loop that goes from 1 up to 4, well, the C++ compiler will generate code that accesses a sub 1. In this case, we are multiplying a sub 1 times 3, so that 3 there is going to be replaced with a 9. Then we move to the next subscript, which is 2, and we change the 5 to a 15. Okay, notice that for each item in here, we're multiplying each one by 3. So this 3 is going to become a 9, this 5 is going to become a 15. This 7 will then become a 21, and when we get out here, notice that our test is I less than or equal to 4. We're going to access a sub 4, and we're going to multiply a sub 4 times 3. Now, because C++ stores values in ascending contiguous locations, the compiler is going to assume that what I want to do is to modify this integer's worth of storage here to contain 3 times the value that it currently contains. Now, this is actually 4 bytes of memory, 1 int's worth of memory following the end of the array A. But heck, I'm going to take whatever that value is, multiply that value by 3, and then put that modified value back in that position. This may accidentally work. That is, it may be that you can grab the value in that position, multiply it by 3, and put the revised value back, and the program won't even notice. Your program will continue chugging along and behave successfully. Another possibility is that the program will crash immediately if that integer's worth of memory is being used for some other kind of important object or variable. And yet a third possibility is that the program will appear to be working okay for a while, and then at a certain point start producing garbage values or perhaps crash. Why in the world does C++ not do array bounds checking? Well, the answer again is speed. Anytime that there is a choice between speed and safety, C++ always chooses speed and leaves it up to the programmer to do what is safe. Is this good or bad? Well, it's a fact of life. The assumption in the C++ language is that you want the code to be as fast as possible, and so you don't support overhead costs involved in safety checking. Okay, so here is a possible output from this code that we've written here. A is an array of 4 elements, specifically each of those is type int, initialized with 2, 3, 5, 7. This loop is mistakenly going through subscripts from 1 to 4 rather than from 0 to 3. And so these values are being changed to 9, 15, 21, and then 3 times whatever is in that location. If the program hasn't crashed at that point, then this next for loop will run and also use the same mistaken sequence of indexes, 1 through 4, and display those values to the screen. So our output might possibly look like a sub 1 is 9, a sub 2 is 15, a sub 3 is 21. Those are the good values of a, and then we might get a sub 4 is some garbage value. If we look at our output carefully, we may notice that that looks awfully fishy, and we may realize that we've created a bug in our code. But sometimes we just overlook things like that and only discover the problem later. Okay, well, what about the for loop? The for loop, as I said here, has 4 parts to it. There's the initialization part. Then there's the test part. If the test is true, we do the body part of the for loop. And after the body has been performed, we execute the change expression. All right, that's the 4th thing that happens. After the change expression has been evaluated, we then loop on the test and the body and the change and the test and the body and the change until eventually the test becomes false, at which point we fall out of our loop. Now, it turns out that any of the 4 parts of the for loop can be left out. For example, if you don't have a test expression, C++ assumes that that test expression is always true. And so the accepted way of writing an intentional infinite loop that does nothing forever is to just write a for loop consisting of the word for and then parentheses, 2 semicolons separating an empty initialization from an empty test. The empty test is true, from an empty change. And here we have an empty body. And so this for loop will just run and run and run and run forever, doing nothing at all. It just occurred to me, by the way, I didn't say this aloud, and I probably should have, that you must have exactly 2 semicolons in the top part of your for loop. Those 2 semicolons are absolutely required. If you use commas instead, that's an error. If you use colons instead, that's an error. If you only have one semicolon, or if you have 3 semicolons, that's an error. You must have exactly 2 semicolons separating the initialization part from the test from the change. Now, at the bottom of slide 21, again, we have an infinite loop. This infinite loop is actually doing something. It's just going to display hello world over and over and over again until eventually the user gets sick of it and presses Control-C to kill the thing off. In this loop, on slide 22, we have an example where the initialization part is left empty, because what we're doing here is we're asking the user to enter an integer as input. We're using getLine to read that line of text from the user's keyboard, and then we are getting our integer value for j by converting the string s to a C-stir, and from there converting that sequence of characters to an int. A to I is ASCII to int. Okay, so the initial value that we want for j is coming from this A to I function call. Consequently, there's nothing left to do in the initialization part here, and we can just go right to our test. J less than 10, display j, add 1 to j. As long as j is still less than 10, display j, add 1 to j. So if we run this code and we ask the user to enter an integer and the user types a 0, this loop is going to end up running exactly 10 times because we'll display 0 and then 1 and then 2. When we get to j equals 10, we're going to stop. So this will end up displaying 0 through 9 if the user types a 0. On the other hand, if we ask the user to enter an integer and they type 20, well, 20 is already not less than 10, and so we're going to get no output except for this final new line character. Okay, so again, just to summarize, an empty test is true. An empty init simply doesn't do any initialization. The change may also be empty if whatever needs to be changed has been accomplished within the body of the loop. That sometimes happens. Sometimes you need to modify and test more than one loop variable. Since I have just told you that you have to have exactly 2 semicolons in the structure of the for loop, that is, you have the initialization part and a semicolon, the test part and a semicolon, and then the change part, how could you modify 2 or more variables or test 2 or more variables in the for loop? Well, turns out that you can use something called the comma operator to separate the multiple changes that you need to do or the multiple initializations that you need to do within the loop. Here's an example. I have j is an int initialized with 0. X is a double initialized with 2.2. Now, because I've initialized j and x right in their declarations, and they're so close to the for loop that I don't have time as a coder to forget what I've done, I'm not bothering to do any initialization. The initialization part here is empty. I am then testing whether j is less than 10. If j is less than 10, I'm going to display the value of j, which the first time through is going to be 0. Then I'll display a horizontal tab, and then I'll display the value of x, which is 2.2. Now, after I have performed the body, in the change expression, I want to do 2 things. I want to increment j from 0 to 1. I also want to multiply x by 2. And I can do that by sticking a comma in between those 2 expressions. Okay, so j will be incremented first, and after j has been incremented, x will be multiplied by 2. Since 1 is less than 10, I'm going to display 1 and 4.4, and then go back and do my change, and I'll display 2 and 8.8, and so forth. The output will look like what's shown here on slide 25. Okay, so we have taken a look at arrays and we have taken a look at for loops. For loops are often used for stepping through elements within an array. Of course, for loops can be used for other iterating purposes as well. Okie doke, so that gets us to the end of lecture 5.